And now I'm going to share my screen. All right. So this is section 1.1 that I'm covering. So if you haven't gone through 1.1 before, then you really don't need to after you've watched this video, because I'm basically going through it for you. I'm not going to go through tons of examples, but hopefully enough that you have an idea of what's going on. So that's the goal here. So I'm going to just start with some definitions. So we've got, these all come from the textbook, so basically what a fraction is. So fractions are numbers of the form a over b, so they have that vertical or horizontal bar, where a over b equals a divided by b. So the key thing here is, oops, I accidentally hit the slide to transition. The key thing is that a fraction is also indicating division. So you can always convert division problems into fractions and fractions into division. Sometimes it's easier to think about it as division, sometimes it's easier to think about it as a fraction, but they're interchangeable. And we have to make sure that the denominator, which is at the bottom of the fraction, is not 0, because we can't divide by 0. Dividing by 0 equals undefined. So whenever we have fractions, we can't have 0 in the denominator, but you can have 0 in the numerator. 0 on top is completely fine. So the top is called the numerator, D is called the denominator. If you're confused about which one is which, I think of denominator as down, and so that tells me that it's the bottom one. There are 3 different classifications of fractions. So we have proper fractions, where the top is smaller than the bottom. So they use these words like the numerator and the denominator, but I frequently just say top and bottom because they're shorter. That is the less than symbol, so the top is less than the bottom. That is a proper fraction. An improper fraction is if the top is equal to the bottom, or if the top is greater than the bottom. That's an improper fraction. And then we've got mixed numbers, which is a whole number and a fraction. So it's a whole plus a proper fraction. So that's like 2.5 would be considered a mixed number. So it's mixed out of whole numbers and fractions. Generally in algebra, we don't write things in mixed numbers. So we usually use improper fractions and proper fractions. And we do that because improper fractions are just a lot easier to work with than mixed numbers. So whenever you give your answers, it's completely fine to give your answer as an improper fraction. You don't have to convert it to a mixed number. And I'm not even going to show you how to convert things to a mixed number, because we just don't really work with them that way. We usually just do proper or improper fractions. So in order to understand fractions and simplifying fractions, we need to talk about something that's called prime factorization. So prime factorization is the process of writing a number as a product of primes. So you may wonder, what does that mean? So first off, the word product means multiplication. So algebra and math is it's really another language, and learning math is just like learning another language, and that's usually why it's harder when you're older, because learning languages are harder when you're older. There's actually a recent study that found that the language part of your brain doesn't even talk to the math part of your brain. It's harder for them to connect, which makes it even more harder. So part of being successful at learning algebra is learning the language, the symbols, the grammar. So when you see the word product, that means multiplication. So prime factorization means we're writing a number as primes multiplied together. So that's what that means. And in order to do that, you need to understand what a prime number is. And so this is the thinking process here that I'm going through, or saying, oh, okay, product of primes. What does a product mean? Okay, now that I know what a product means, what does prime mean? This is how you should go through a textbook or reading anything with math. If there is vocabulary you don't understand, look it up, figure out what it means, and then try to rephrase it in a way that makes sense to you. So I'm trying to emulate that process here so that you can learn how to read math and then translate it into everyday terms. So we're multiplying primes together, so we need to know what a prime number is. A prime number is a number that is only divisible by itself and 1. So divisible means that if you were to divide that number by something, you get a whole number. We call that divides evenly. So like if we take the number 6, so 6 is not prime. And the term for that, we call it composite. And 6 is not prime because we can divide it by 1, we can divide 6 by 2, we can divide 6 by 3, and we can divide 6 by 6. So that's what means that it's not prime, because there are many numbers we can divide into 6. So 1, 2, 3, and 6 all divide into 6. So a prime number is one where it doesn't have things that go into it. And 1 doesn't count because prime numbers divide by itself and 1. So 1 doesn't count. But anything larger than 1 counts. So 2 is a prime number. 3 is a prime number. 4 is not, but 5 is. Then 7. And then the next prime is 11, 13. And you just think of what numbers do you know that don't have anything that divide evenly into them, and those are your prime numbers. So when we're writing something as a product of primes, we're writing it as these numbers, these special numbers multiplied together. So that's what we mean by prime factorization. Now the next term here is a factor. So a factor of a number is also known as a divisor of the number. And a divisor means it divides into it. So, oops. These numbers 1, 2, 3, and 6, these are divisors of 6 because they divide into 6. They are also called factors of 6 because if you multiply these with another number, you can get to 6. So like 2 times 3 gets you 6. So 2 and 3 are factors of 6. 1 times 6 multiplies to 6. So 1 and 6 are factors of 6. So the word factor is going to be coming up a lot. And if you have to go on to college algebra, it's going to come up every single week. So it's really important to understand what that means. So now you have sort of an idea of prime factorization. We're basically taking numbers that divide into our overall number, and we are writing them as multiplication. That's what we're doing here. And the reason why you might want to do this is it's helpful for reducing fractions. It's helpful for finding common denominators of fractions. And something that's not fraction related is factoring out the greatest common factor. And that's something we will look at in the second half of the class. So you'll be doing prime factorization later in the class in addition to this week. So are there any questions so far?
Not yet.
Okay. If you have questions, just go ahead. You can click the hand thing or you can type your question. So I'm going to start with an example here, and we're going to do prime factorization for both of these numbers. And I do what is called a factor tree. It's basically I'm taking my number and I'm branching out into pairs, and then I keep branching out until I can't go any further. In order to do prime factorization, you do want to have a calculator handy so that you can check your make sure you know what divides into it. So I'm going to start with 70. So I am going to say, okay, what two numbers can I multiply together to get to 70? And there are multiple ways to get to 70. So it doesn't matter what two numbers you start with. Somebody tell me, what are two numbers that multiply to 70?
7 times 10.
7 times 10, exactly. Well, I being a little sensitive today. So what I'm going to do is I'm going to just kind of branch this out, and then I'm going to write 7 and 10. And then I'm going to say, are any of these prime numbers? So 7 is a prime number because we can't divide that by anything. So I'm going to circle that. I circle it just so that I know that that branch is done. Then I have 10. Well, 10 I can split up further. So 10 only has 2 and 5. 2 times 5 gets you 10. So I'm going to write 2 and 5. And so I'm going to circle the 2 and I'm going to circle the 5. And because those are prime numbers, I can't divide 2 by anything. I can't divide 5 by anything. And when I have all the bottom parts circled, I am done. So that is my factor tree. The prime factorization is writing these multiplied together, and you want to do it from order of smallest to largest. So that's 2 times 5 times 7. That's what the prime factorization is. And I use a dot to indicate multiplication. Never use an X for multiplication once you start doing algebra, because we're going to be using X to represent a variable. So just going forward, never use an X, use a dot to indicate that you're multiplying things together. So that's just otherwise you would lose points basically, because then it starts getting confusing on what your symbols mean. So always use a dot. So that's the prime factorization of 70. Now let's look at 136. So 136 is not, usually people only know their times tables up to 10, and that's going to be 136 is beyond that, and I don't know my numbers that multiply to 136. But what I do know is that 6, the last digit, is even, which means I can divide this by 2. And this is where the calculator comes in. Oh man, it's really sensitive. So I'm going to split this up, and I know that I can divide 136 by 2, and 2 is prime, so I'd circle it immediately. So then I'm going to take my calculator and do 106 divided by 2. Yeah, that gives us 68. So now we need to split it up again. 68, off the top of my head, I don't know what multiplies to 68, but I know that 2 goes into 68. So I can split that up again as 2, which is prime. Divide 68 by 2, we get 34. So 34 is even, so again, I know that 2 divides into 34, and that one I happen to know is 2 times 17. So that is 2 and 17 is a prime number. So now I have basically branched out as much as I can, and now I just have my prime numbers circled. So when I write the prime factorization, this is 2 times 2 times 2 times 17. Or if you have repeated multiplication, you can use exponents. That's 2 multiplied 3 times, so the exponent is 3 times 17. So both of those are valid answers, but when we're reducing fractions, the first way is easier to work with. So are there any questions on the prime factorization process or on the 2 examples that I've done so far?
It seems pretty easy.
Yeah, it's not too bad so far. So next is how we're going to actually use this, and that's with simplifying fractions. So the process of simplifying or reducing a fraction. So just if we say reduce a fraction, that means we're trying to make the number smaller. And if you see the word simplify, reducing is part of that process. So simplify is a math word that we use that means a lot of different things. Reducing is one of those. So if you're simplifying and you end up with fractions, you always have to reduce. You're never done until you've reduced your fractions in the end. So we simplify using these basic rules. The fact that anything divided by 1 is equal to itself. The fact that anything multiplied by 1 is equal to itself. And the fact that anything divided by itself is equal to 1. So just special rules regarding the number 1. And so this is from the textbook. This is the fundamental principle of fractions. So it says, suppose the number C is a common factor in the numerator and denominator of a fraction. So let's break that down. Common factor, which means that it's a common, means it's in both the top and the bottom, and it's a factor, which means it's multiplied. So you can see that's what we get in this first. We have A times C and B times C, and the book's using the X, and I hate that they're doing this because it's just going to confuse you later, but our textbook's using X. So if it's basically what we're doing here is if the same thing is multiplied on the top and the bottom, we can split this up into 2 fractions. So you would have your things that are not the same times the things that are the same. And so C over C, that's division. Anything divided by itself is 1. That's that last thing right there. So that allows us to replace that with 1. And so then when you multiply by 1, that gets you the same thing. So anything multiplied by 1 is equal to itself. So we're using those 2 bottom rules for this fundamental principle of fractions. And I use the top rule in an alternate way to show how to simplify fractions. So let's actually do this in yeah, go ahead, ask your question.
Okay, it's kind of confusing for me when it be with the letters because I struggled through this all the way through high school and I still don't get it.
So these letters, these are called variables. They're just representing any number you want. So just pretend they're numbers if it makes it easier for you. So if I say, instead of A, let's say I have 1, and let's say I make B 2, and then let's say C is 3. So this would be the same thing as I had 1 times 3 over 2 times 3. So I'm just rewriting this as 1 over 2 times 3 over 3. So 3 divided by 3 is equal to 1. So
okay, so anything divided by 1 equals to itself. So
yeah.
Okay, I think I get what you're saying. So anything divided by 1 is equal to itself. So that means that you got your 3. So this 3 times 3 is going to equal to that 1 because it's 3 divided by 3.
3 divided by 3 equals 1, yes. Yeah, so if you see things with the letters, if you replace it with numbers, yeah, sometimes that makes it, yeah. So anything divided by itself, that's 3 divided by 3 right here. That's an example. I can write it as a fraction, or I can write it as the division symbol. And so that is equal to 1. Does that help?
Okay, I gotta get it now.
Okay, yeah. Are there other questions?
I mean, it's a question, but it's dealing with something else.
Okay.
It's dealing with this.
What is it dealing with?
It's dealing with the assignment.
Okay. So assignment questions. I have you. How about you email me those, and then I can address that separately, because I want to make sure that I go through all of the fraction stuff together, and this is probably going to take a while. So if we have time at the end, if we haven't spent a lot of time, I can answer that then. But I want to make sure I get through everything through here first. Does that work?
Okay.
Okay. So let's actually simplify some fractions. So this is my second example. I'm going to simplify 8 over 12 using the prime factorization method and the division method. So I'm going to show you the two ways that you can use to reduce fractions. So first is the prime factorization method. This is the method that the book is teaching you. So I'm going to label this as book method. So in order to use this method, you have to do the prime factorization for each number, the top and the bottom of the fraction. So 8 is 2 times 4, and 2 is prime. And then 4 is 2 times 2. So my prime factorization of 8 would be 2 times 2 times 2. Now 12, well, that's 3 times 4. Otherwise, I do 6 times 2. It doesn't matter. Yep, you can do 2 times 6. You'll get the same answer in the end. And then...
And 4 is 2 times 2.
Yep. So the way the book does this is that we have 8 over 12. So 8, if I write the prime factorization, is 2 times 2 times 2. 12 is 2 times 2 times 3. And then what you can do is anything that's the same on the top and the bottom, you can cross out. So I have a 2 on a top and a 2 on a bottom. I have another 2 on top and a 2 on the bottom. And so you cross out things that are the same. That's that property that 2 over 2 is equal to 1. So we're basically removing all the things that are 1. And then all we have left is 2 times 2 and 3. So that's our answer. So that
I
is...
just said that when I looked at 8 over 12.
You're like, oh, that's 2/3. Yeah, I picked a simple one here. I'm not like, I mean, you can get some really nasty looking fractions. So that's the prime factorization method. That is the method that the book is basically teaching you. There's also the division method. I use both methods depending on just how I'm feeling. And so the division method is just saying, well, what number can I divide from each thing? So if I say what number goes into both 8 and 12? Can you say that again?
4.
2 or 4, exactly. It doesn't matter which one we pick. I like to pick the bigger one because it's faster. So I can divide the top by 4 and the bottom by 4.
And
I'm basically dividing it by 1. Yeah, 12 divided by 4, so you're going to 3 in the denominator. And then 8 divided by 4 gives 2. And you get the same answer.
I think I like them better.
That's why I show both methods, is because the book shows you the prime factorization. But if you know your division, the division method is faster. I usually use prime factorization if I have really big fractions, because those you may have to divide multiple times until you are reduced all the way. So sometimes, like the 8 over 12, we could have also divided it by 2. So 8 divided by 2 is 4, 12 divided by 2 is 6, but then you have to do it again. So sometimes the division method means you have to do it more than once to get down as far as you can. It depends on what numbers you pick. So if you have really big numbers, using the division method could be a slow process, and sometimes then prime factorization is easier. Are there any questions on this slide?
No.
Okay. So now I've got two other examples here. And the first one here is an improper fraction because the top is larger than the bottom. And then the second one here is a proper fraction. So you can use any method you want to reduce these. So I know we've got...
classes start, I actually...
Mm-hmm.
Before classes start, I actually did all that. I researched all the division, dividing property, dividing fraction, adding fraction, subtracting fraction, and proper fraction. I did all that, and I did great. So
Awesome. Usually it's hard for a lot of people, so that's good. So this 20 over 12, so we can reduce this any way you want. We can do the prime factorization method, or we can do the division method. And actually, so Blackboard Collaborate here allows me to create a poll. So I'm going to create a poll, and I'm going to ask you guys, which method do you want me to use? Prime factorization or division? So that poll should now be popping up on your screen, and then just click which method you want me to use to do these. Okay, so we've got two people for prime factorization so far, 5 for division. I'm trying to, so let's see, I feel like I should do both, but I'm trying to decide which one would be the best one to do prime factor. Let's do the prime factorization on the first one because that's smaller numbers, and then I'll do division method on the second one. So that way you can see both again. All right. So I'm gonna pull up my. So let's do prime factorization on the first one. So that means 20. I need to start splitting up. So 20 is 4 times 5. 5 is a prime number. And then 4 is 2 times 2.
I was way off. I was thinking 10 times 2.
Oh, you can do 10 times 2. That's going to get you the same answer. I'll do that up here. So if you do 10 times 2, and then 10 is 2 times 5, you still have 2 2's and a 5. So you get the same answer. So use whichever numbers come to your head first. There's no wrong way to do prime factorization because you'll get to the same answer. So 12, last time I did 12, I did 3 times 4. So let's do 2 times 6.
2, 6.
So 2 is prime. And then 6.
2 thirds.
2 times 3. So now I'm going to rewrite this. I have 20 over 12. 20, if I write all of these numbers multiplied, it's 2 times 2 times 5. 12 is 2 times 2 times 3.
2 times 3.
So then I can start crossing out things that are in common. Yep. And then, yep, we got 5 over 3. And that's the final answer there. So actually, that was less interesting than I thought it was going to be because that came out to be still all the 2's canceled, but that's okay. So that's the prime factorization method. Now let's do the second one with division. So we want a number that I can divide out of 35 and 80. What number can divide into both?
35 and... is it 5?
Yes. So the rule, if things are divisible by 5 if it ends in a 0 or a 5. So, oops. So that means, oh man, it's just all over the place here. I'm just trying to draw. So I can divide both of these by 5.
That'll be 16.
So 35 divided by
That'll
5
be
is
8 divided by
7.
5 is 16.
80 divided by 5, I'm using my calculator. My calculator
That's
says that it's
16.
16, yes. Now, 7 is prime. So the only thing that divides into 7 is 7, but 7 does not go into 16, so that means that's the only thing we can reduce out. So that's as far as we can go there. So reducing fractions is not bad. All you really need to know are your multiplication and division. And if you and as long as you know like your times tables up to 10, which most people know still remember because that's drilled into us in elementary school, it's really not so bad. You don't even need a calculator most of the time.
And then also they got me a composite book that you know the little notebooks that you buy. Composition.
Oh, composition. Yeah. So now let's talk about multiplying fractions. Now that we have looked at reducing. So when you multiply fractions, you multiply straight across. So no diagonal multiplying, it's straight across. And then you always reduce whenever possible. So you multiply the tops of the fractions together and the bottoms of the fractions together. So multiplying fractions is actually really easy. All you have to do is just literally multiply what you see.
I'm actually ahead. Like I did division and multiplication. I'm actually ahead.
So this example here, I've got a multiplication problem and I'm going to show you that you can do it 2 different ways. So you can do the multiplication first and then reduce, or you can try to reduce first and then multiply. So it depends on which method you prefer. So I'm going to start with the multiply then reduce. So we have 10 over 13 times 26 over 15. So when you multiply then reduce, you're multiplying the tops together. So we're doing 10 times 26 and we're doing 13 times 15. This you definitely need a calculator, especially I can do 10 times 6. That's 260, but 13 times 15 I don't know off the top of my head. So my calculator gave me 195. So we multiplied, but now we need to reduce that number. These are big numbers. I could do prime factorization, or I can just make a guess and say, oh, well, let me try to divide those by 5, because 5, I know that 5 goes into both of these numbers, and then I can see what happens. So I'm going to divide both of these by 5 to try to reduce these.
260 divided by 5 is 52.
Thank you.
Divided by 5 is 39.
39. Okay. So now we've got 52. Oops, what did I just... My computer is all over the place today. So I'm going to just kind of move this over here because 52 over 39 actually still reduces. So I look at those numbers and I play a lot of card games. And I know that in a deck of cards is 52 and each suit has 13 cards. And I know that 3 gives you 39 if you have 3 suits. It's just I know my 13s because I play cards. So I know that each 13 divides in both of these. I actually recently was at a conference where they were talking about that people like younger kids, like those that are still in high school, they don't play cards anymore, so they don't know how many cards are in a deck of cards, like that there are 52 cards in a deck of cards. And I'm just like, oh my goodness, like I played a lot of cards growing up. So 52 divided by
52
13
divided by 13 is 4. 39
and
divided by 13
is 3. Yep. So there. So we multiplied those together and then we reduced it. And I know that my work is kind of all over the place, but we got the right answer. So we got 4/3. So now I'm going to show you what I usually do, because I usually try to reduce first and then multiply. So how that works, oh goodness gracious. So I'm going to start with the same problem, 10 over 13 times 26 over 15. And I try to do division before I do anything else. So like I see 10 and 15, I know I can divide 5 out of those. So I'm going to write this down, and I'm going to divide those both by 5.
Divide by 5 is 2. Divide by 5 is 3.
So I'm going to set up my fraction. So I have 2 on top, and then 15 divided by 5, that's 3. And I can do the same thing with the 26 because I know I can divide that into 13. So I can divide both the 26 and the 13 by 13 because I just look at those and I'm like, oh, I can divide both of those numbers.
26 divided by 13 is 2.
And then 13 divided by 13
divided
is 1. So if I reduce first, I now have much smaller numbers, and now I can multiply those. 2 times 2 is 4.
2 times 3 is 1.
And 1 times 3 is 3. So you get the same answer. And I prefer this method because you're multiplying smaller numbers, and it just seems like less steps. So you can do either method, but some people get confused by the reducing method. That's why I try to color code so that you don't get confused. So it's up to you on which method you prefer to when you multiply. You can either multiply first and then reduce, or you could try to reduce first and then multiply. Are there any questions on this particular slide? All right, so let's move on to dividing fractions. So we have to talk about what it means to be a reciprocal. Two numbers are reciprocals if they multiply to 1. So an example of this is if I have 1/2, if I multiply that by 2, 1/2 times 2, that is equal to 1. Those are considered reciprocals. Another example is 2/3. If I multiply that by 3/2, that also gives me 1, because when you multiply, we'd have 2 times 3, which is 6, 3 times 2, which is 6. So when you multiply those fractions together, you'd end up with 6 on the top and the bottom. 6 divided by 6 is 1. So we call things reciprocals if they multiply to 1. And if you notice, they're basically flip-flopped. So 2 over 3 and 3 over 2, they're flip-flopped. Those are reciprocals. 1/2 times 2, you can always write whole numbers as fractions. So if I wrote 2 as 2 over 1, now you can see they're flip-flopped. So in order to divide fractions, we are multiplying by the reciprocal because division is actually defined as multiplication. So you take your fraction that's after the division sign and you flip it, and then you multiply.
So 2 over 1 would be 1/2?
Yeah, the opposite of 2 over 1, the reciprocal of 2 over 1 would be 1 over 2. So you're just flip-flopping the top and the bottom. So let's take a look at this example 5 here. So the first one here, I have 7 over 25 divided by 1 over 5. So that is a division problem, but we can turn it into multiplication by taking what's after the division symbol and flipping it. So that'd be 7 over 25. When you do this, you turn it into multiplication, and then you have 5 over 1. So then you would multiply those. 7 times 5 is 35. And 25 times 1 is 25. Now we do need to reduce this. And we can divide them both by 5. Because 35 and 25 can both be. And so, yep, we get 7 over 5 as our answer. So every division problem is actually a multiplication problem. It's just one extra step, essentially. Now, the 12 over 5 here on the right, so it's divided by 4. If you have a whole number, you can always turn it into a fraction by writing it over 1. So I'm going to first rewrite that division as 4 over 1 instead of 4. Because that way when you flip it, you flip to multiplication and then it becomes a 1 over 4. So then we can multiply straight across. 12 times 1 is 12. And 5 times 4 is 20. And then we want to reduce 12 over 20.
Okay, both divided by 4?
Yep. So I'm going to divide them both by 4.
That's 3/5.
Yep. 12 divided by 4 is 3. 20 divided by 4 is 5. That's exactly right. 3/5. So, are there any questions on the division of fractions here?
No.
Okay. Anybody else? I know we've got several people that are on the chat as well. I don't see anybody writing anything or typing anything, so. Next, we get to go to adding, subtracting, but first we need to talk about the common denominator, which you can also call the least common multiple of the denominators. So, when you add and subtract fractions, they need to have a common denominator. Common means the same, denominator means the bottom. So the number in the bottom needs to be the same. In order to do this, we have to create fractions. Like if we have two fractions and their bottoms are not the same, we have to make them the same. And so we do this by using the rule that we can multiply by 1 and we haven't changed anything. So anything multiplied by 1 is equal to itself. So we're basically going to be reversing the reducing process in order to build fractions up so that we can add them. So the value we want in the denominator is called the least common denominator, or it's sometimes called the least common multiple of the denominators. So the book is telling you how to do this via prime factorization. And I will demonstrate that process because it will make more sense than what's written in the book. And then I'm also going to show you how you can do it with multiplication. So we have the number 12 and the number 30. We want the least common multiple. So least means smallest. Common means the same or what they have in common. So you're thinking of divisors. Because we're looking at multiples means numbers that are bigger than these. So we're looking for the smallest number both the 12 and 30 can multiply to or divide into. So we're actually looking for a bigger number. Kenya, I see that you've raised your hand. Do you have a question? You can type it in the chat box if you have a question. If you
My bad, I'm
expand,
sorry.
oh, it was just accident. Not a problem. All right. I just want to make sure if people have questions, they ask them. So we're looking for a number bigger than 12 and 30. So we're going to do this first with prime factorization. So I'm going to do the prime factorization of 12. We've done this multiple times. Oh man, it really likes to, oh, I went too far. Okay. So 12 for me, I always do 3 times 4. On 4 is 2 times 2. And then 30. So 30.
No, you said small, so they'll be.
Well, we could do 3 times 10 with the prime factorization. And then 10 is 2 times 5. Oops, I circled 10. That is not a prime number. 10 is 2 times 5, and 2 and 5 are prime numbers. So to find the least common multiple, we're looking for something bigger than what we started with. So I'd like to write these down and sort of make a table or a column here. So 12 is 2 times 2 times 3. And then I'm going to try to line this up. 30 is 2 times 3 times 5. So, and I'm lining them up. And then I'm going to just,
I got a
yep.
question. So you for the least common, I mean the least number they have in common, like the smallest number they have in common.
No, so it's the least common multiple. So it's the smallest number they both multiply to.
So would 2 be it? Because
so 2 is the smallest number that divides into these numbers. That is actually called the least common divisor. The least common multiple is going the other way. These numbers are going to multiply to this bigger number. So we are trying to build something that's bigger. We want a number that I can divide by 12 and 30, but I want the smallest one that can do that. That's where the word least comes in, but it needs to be bigger. Kenya, do you have a question?
My bad. Would it be 60?
4 times 3 is 12 times 5. Yes, it is 60. So, yes. So the way that I find this with prime factorization is I line them up, and then I write down all the numbers that I have in order. And if it shows up twice, if they're lined up, that's fine. So I have 2 times 2 times 3 times 5.
oh, I get how y'all getting that.
So then when you multiply all those together, so 2 times 2 is 4, 4 times 3 is 12, and 12 times 5 is 60.
12 times 5.
So the 60 is considered the least common multiple. So it's bigger than both numbers, but it's the smallest number that they have in common when you go through the multiplication table. And so that's sort of the second method. If you don't like the prime factorization method, is to do a multiplication table method. So the multiplication table method, I start with my numbers. And this is basically times 1. 12 times 1 is 12. 30 times 1 is 30. And then I'm going to multiply these numbers by 2. So 12 times 2 is 24. And 30 times 2 is 60. Oops. So now I'm going to do times 3, and I'm going to keep doing this until I find a number they have in common. So 12 times 3 is 36. 30 times 3 is 90. Still nothing in common, so now I have times 4. 12 times 4, 48. 30 times 4 is 120. Still nothing in common, so then I do times 5. 12 times 5 is 60. And now I have found the first thing that they have in common. And it's the smallest number they have in common in the multiplication table. And so that's why 60 is the least common multiple. So this method, the multiplication method, I think makes sense with the name, but I feel like the prime factorization is a little quicker than just keeping to multiply things together. But do you have an idea of what it means to be the least common multiple now?
Yeah.
So we're going to use this concept when we're trying to get a common denominator when we're adding subtracting fractions. So adding subtracting fractions. Basically, you need to have the denominators the same, and then you only touch the tops, the numerators. So you're either adding the tops together, or you're subtracting the tops, but you don't add or subtract the bottom. The bottom stays the same. So that's essentially what this little thing from the book is saying. So first I'm starting with two examples where they are the same, because that way you can see how this works without trying to throw in common denominators. So if we have 9 over
would
5,
that be 10 over 5?
yes, because you do 9 plus 1, so that is 10 over 5. And 10 divided by 5 is a whole number, that's 2. So your answer here is 2. Then when we have 11 over 18 minus 5 over 18, you're subtracting. Yes, so 11 minus 5 is 6. The 18 stays the same, and now we want to reduce. So most people liked the division method. I can divide both of these numbers by 6, because I know that 6 goes into 18.
6 divided by 6, would it be 1? Then 18
Yep.
divided by 6.
So we get 1,
That'll be 3.
3. So you get 1/3 as your answer. So when there's a common denominator, adding and subtracting fractions is really not that bad. You're just adding and subtracting, and then you do have to do a little division for reducing, but otherwise, it's really, a lot of people are terrified of fractions, and it's really not so bad because you're just adding, subtracting, and then doing some multiplication division. That's like all you're doing. It's really not so scary. So let's take a look if they do not have the same denominator, because then we have to figure out what our common denominator is going to be. We want to find the least common multiple. So the least common multiple, we usually abbreviate this as LCM. Or if you're looking for a common denominator, you might see it abbreviated as LCD for the least common denominator.
Yeah.
So we want the smallest number that 16 and 2 have in common when you look at multiplication tables. 32, they both have 32 in common. 32 is actually not the smallest, but that's okay because we don't actually have to find the smallest. We just have to make sure they both have something in common. So we'll work with 32. So how this works is I'm going to leave some gaps here. We want to make the denominator 32 because we know they have 32 in common. They can both multiply there. So 16 times 2 gets you to 32. So I'm going to have to multiply 16 by 2. But our rules say I have to also multiply the top because I can only multiply by 1, so I have to do the same thing on the top as I do on the bottom. Just like with reducing, you have to divide by the same thing on the top as the bottom.
Would that be 6 over 32?
Yeah, that's going to be 6 over 32 there. Then the 1 over 2, to get to 32, I need to multiply 2 by 16. And so I have to do that on the top and the bottom.
So 16 over 32.
Yes, so we have 6 over 32 plus 16 over 32. And now they have a common denominator, so now that you can add those. 6 plus
Between
16.
2 over 32.
Yep. And now we have to reduce. 22 and 32 both can be divided by 2. So I'm going to rewrite this.
That'd be 11. 11 over 16.
Yep, we got 11 over 16. And 11's prime, and 11 doesn't divide into 16. So that is our answer there. 11 over 16. So now let's look at our other one here. We have 35 and 10. So again, we want to have a common denominator out of 35 and 10, something that we can build them both back up to. Ideally, we want the smallest number, but really any number works as long as you can get them both in common. So what would be... So 5 divides into them. We're looking the other way. We want a number bigger. We have to multiply to this bigger number.
70.
70. Yeah, so we can get to 70 as a common denominator. It's really easy to accidentally go in the wrong direction and want to give the smaller number. It's very confusing.
Indeed.
Whoops. So I need to build these up to 70. And I've got a minus here, and I'm leaving some gaps so I can fill in what I'm multiplying by. So let's just make it a light blue. So 35 times 2 gets me to 70. So that means I have to also multiply the 12 by 2.
That'd be 6.
Oh, that's dividing. We're multiplying here.
Oh, multiply.
Yeah, it's so easy. You get to get confused and to accidentally do the opposite. So math is all about the details. You really got to pay attention to those details. And then 10 to get to 70, we need to multiply that by 7. So I need to do that on the top and the bottom. So 12 times 2, 24 over 70, and 7 over 70. And so then we do 24 minus 7.
That's 17 over 70.
Yes. And 17, I'm pretty sure, does not even have anything in common with 70. 17 is prime, so that is our answer there. That one, we didn't have to do any reducing. And I just realized I spelled denominator wrong. I am not an English teacher. I'm not all that best at spelling. Oh man, it really wants to keep changing screens on me. Denominator. There we go. Okay, now I've spelled that correctly. Are there any questions on these two examples on how you add and subtract when the denominators are different?
No.
Okay. So I know that we've hit about an hour, but I've only got just 2 more examples left and I'm done. So if you guys are willing to stick around a little bit longer than an hour, even if you're not, you can always pop off. These are recorded, but so I'm almost done here. We need to talk a little bit about mixed numbers and improper fractions. So as I mentioned at the beginning, in algebra, we really don't work a lot with mixed numbers. We usually work with improper fractions. You can do math with mixed numbers, but you always have to think about if you have to borrow from the whole number to get to the fraction, especially when you do subtraction, and it's a lot to worry about, and it's just not fun. So the best way to do anything with mixed numbers is to make an improper fraction first. And so this is really tiny here, so I'm going to write this bigger. Basically, what you do is if you have 3.5, you multiply the whole number by the denominator. So you multiply the 3 times 2 together, and then you add the 1. So 3 times 2 is 6 plus 1 is 7, and that is your new numerator, and then your denominator stays the same. So that's how you convert a mixed number to an improper fraction. It's the whole part times the denominator plus the top. So I've got 2 examples here, one with multiplication and then one with subtraction. So the whole reason why you want to make these improper fractions is because your brain says, oh, let me just do 2 times 1 and then let me just multiply the fractions. If you do that, you're going to get the wrong answer. So that's why it's like, don't even try to work with mixed numbers, because if you try to do what your brain tells you to do, it's going to be wrong. So we want to make these improper fractions. So the 2.5, that's 2 times the denominator 2, so that's 4 plus 1, so that's equal to 5 over 2. And then the 1 4/5, that's 1 times the denominator 5 plus 4. So 1 times 5 is 5, plus 4 is 9. And so that gives us 9 over 5. So I'm multiplying the whole number times the denominator, adding the numerator. Now I see this and I'm like, oh, I can cancel out a 5 on the top and the bottom. I'm not even going to try to multiply first. I'm going to just do my canceling. And so my answer is 9 halves.
Oh.
Which, if you wanted to make that a mixed number, is 4.5. But 9 halves is perfectly acceptable as an answer. But if you look at it as the mixed number form, your brain would say, oh, 2 times 1, that's 2. I should have 2 in some fraction, but it's actually 4 with a fraction. So that's why I say, don't try to do it with mixed number form. You're going to make a mistake, and your brain is going to give you the wrong answer. So same sort of thing with the subtraction. This type of problem, if we were to do subtraction with mixed numbers, we would end up having to borrow from a whole number, and it gets really gross. So we're going to make these improper fractions. So I'm going to take my whole number times the denominator. So 5 times 3 is 15 plus 1. So I have 16 over 3 minus, and then, oops. Oh, man. 2 times 4, so 8 plus the 3, 10, 11. So that's 11 over 4.
It'll be 11 over 4.
Now we need to get a common denominator, because they don't match. 12, exactly. So the first fraction, that denominator is 3. I need to make it 12 by multiplying by 4. And then the other fraction, I need to make it 12 by multiplying by 3.
So 64 over 12.
Mm-hmm. And then
3 over 12.
Yep. And then we need to do that subtraction, which I don't want to, 31. Okay. So we get 31 over 12. And you know, there's really no reason to have to write that as a mixed number. You can leave it like that. Don't make yourself do more work than you have to. If you wanted to, let's see, that would be 2 7/12. If you really wanted to make it a mixed number, but there's no reason to. You can leave it like that. And on the homework this week, there is definitely, you are going to get fractions. I believe it's the second one that's going to end up with a fraction. Don't try to make it a mixed number or anything like that. You can leave it exactly as it is. So We've gone through everything that I have planned on fractions. This is basically the whole section 1.1. I wanted to do fractions because fractions scare people. So do you guys have any questions?
Yep.
Can you go back
yeah.
and get the live after you finish
This slide?
the live? Can we go back and look at the whole live in case we miss
Oh
something?
yeah, the whole thing. Yes. Yes. So, yeah, this is being recorded right now, and when we get off and I'm all done here, I'm going to stop record. It does take some time to process, and then I'm going to download it and then upload it to YouTube. And then once I put it on YouTube, then I will put it into the classroom. So if you want to be notified immediately when this happens, then you could either subscribe to my YouTube channel and turn notifications on, or if you have the Blackboard phone app, your Blackboard app will tell you when new stuff is added. Or if you signed up for Remind, I will send a message through Remind. Yeah, and I'll say, okay, I'll send it through Remind and say I posted this in the classroom, so that way you know when it's there. So, and then I will be posting it under the resources section where it says like live sessions and instructor videos. That's where it's going to be saved. So I put the introductions in with the weekly content, but this particular video will be under the live session part. So, and I will also be including the PowerPoint, so that way you can take a look at the PowerPoint again if you wanted to copy things down. So, yeah. Any other questions?
No.
All right. Jada, I know that you had a question on the homework. Since it's been it's been an hour. If you want to email me that separately, and then we can go through that. I don't want to overload anybody's brain with math, because spending an hour on it is a long time. Everybody's gonna need a break. So, you can email me that. But thank you guys so much for interacting, filling out the poll, and this is how I think people learn is by actually being live, like in a classroom and everything. So I thank you guys for being able to attend. It's awesome. So all right, I'm gonna stop the recording, get off here, start processing. So I will get all that going. So you guys enjoy your night. And hopefully you guys have a great Friday and you have a wonderful weekend. And I think I'm doing another one of these. When do I have the next one scheduled? I know I have 7 o'clock on Sunday. I'm going to do sections 4 and or 1.4 and 1.5 where we're adding and subtracting with negatives, because a lot of people really get confused with negative numbers. So I will be doing that 7 o'clock on Sunday. So, all right, I'm going to pop off. So I will talk to you guys later. Thank you so much for joining. Bye.
All right.